Okay, so this video is going to go over electrical capacitors. So capacitors are like our springs from mechanical systems, and capacitors are described by a charge. And they use something similar to Hooke's law to describe their dynamics. So Hooke's law was F is equal to K times D. Well, we're just going to replace all those with their equivalents. So F is going to go to V, K is going to go to 1 over C, and D is going to go to our charge Q. Now the symbol for a capacitor looks like these two lines, these two straight parallel lines here with a C over it. I am using the green here to describe that Q, our charge across this capacitor. And then the capacitor has some sort of current I1 flowing through it. Now, a capacitor is described by Q dot is equal to I1, or VC dot is equal to 1 over C times I1. These two are the same exact things, and you get that from your Hooke's law equivalent here. So the rate of change of charge from the earlier equation is equal to current, just like the rate of change of deformation is equal to velocity. They're equivalents here. So either a charge or a voltage can be the state for a linear capacitor. Now, for capacitors in series, what we do is we take the inverse of each one of those capacitance values, we sum those all together, and we take the inverse of that to get the equivalent capacitance. Now, for capacitors in parallel, we actually just add them straight up all together. And these are derived from, just the energy balances of these elements here. Now, just like springs, capacitors also store something like potential energy. So again, I'm going to put PE in quotes here. And for a linear capacitor, that potential energy is equal to 1/2 1 over C times Q squared, or 1/2 CV squared. They both are the same thing for a linear capacitor. And that's going to describe capacitors.